about introduction to cables. We talked about the cable sizes, how they are used, wherever the application. Now today's topic is about the sizing. How do we size now? After knowing the types of cables, where they are used. Like for example, we said that a 1.0 to 1.5 millimeter squared of a cable is used for lighting. We said 2.5 is used, millimeter cable is used for power. And we also said that 4.0 can be used for cooker, showers. Those are the heavy loads, the washing machines. So when you're doing this installation, you realize that there are different demands for the cable sizes, meaning the type of load of the cable depends on what the cable size that you will use. And we said for the service cable, we normally use between 10 millimeter square to 16 millimeter square. These cables range, and we have different types of insulations in the cables. We have other cables, type of cable called a twin with earth. We have cables like single cables. There are different types of insulation. There are others called armored cables. Like for example, the cables that are used for underground cables, these are called, they have to be armored. This armoring is just some aluminum being inserted in between the cables themselves, so that they can enhance the insulation, so that they can do the mechanical, they can help or assist in mechanical protection. Sometimes you'll realize that these underground cables or even the service cables, wherever they pass through, they can undergo harm or a peeling off of the insulation. So instead of so in order to protect these cables, we use the armoring. We'll be able to look at different pictures that are showing this type of cables. And as we had done the last lesson, I remember talking about the different types of cables that we have. We have the low power cables, like now the internet cables, the data cables, the TV cables. Those are the minor. Those are called the low power cables. So today we want to do the cable sizing, and in cable sizing, we have the IEE regulation wiring code, which is called the BS7671 standard. And this code, this is a cable coding that gives a procedure of the type of cable or of the sizing of cable. When you are doing a design, as an electrical engineer in the electrical profession, you'll get yourself doing a design one time or the other. You'll be doing design, and this design that you'll be doing, you'll be able to calculate. For example, you've been given to design an installation for a 3-bedroom house, and you are told, or even a story house of 3-bedroom units. You are told to do an installation, and you have to calculate the cable sizes. And before you calculate the cable sizes, you have to put so many things into consideration. You have to put the environment, that is the ambient temperature. Is there a lot of heat that can melt the insulation? You look at the loading, the size of load that is going to be used. That is we have also the thermal insulation. Those are the things that we have to put into consideration. So this is a very important topic in the engineering profession, because it is a basics of what you are going to do in the field. So for today, I've said we're going to talk about the cable sizing. And as I start, is that our cable sizing tool is one of the more popular tools on the site. So the tool enables cables to be sized in compliance with the BS7671, the IEE regulation standards, and by implication, the IEC 6364. Those are the regulations that we normally have, which are set. It's called the electrical insulation standards or codes. Okay, so this post now whatever we're going to discuss here gives some insight on how the tool works. So the calculations carried out and how it is used. So with the tool being based on the BS7671, this post will also provide an introduction and explanation of the cable sizing method given in the standard. So the procedure is, we have a flowchart. We will be seeing a flowchart that we use in the cable sizing. So show the general procedure followed by the tool. So number one, some of the things that are being considered in is the current capacity. sorry, a cable size is found which is adequate for the expected current. And then we have the voltage drop. The voltage drop is on a selected cable is checked, and if to be the cable size is increased. And then we also have the fault level. We have to check the fault level that can withstand any disturbance. That is, if not adequate, the cable size is increased. Any errors or warnings generated during the calculations are posted on the user. So, in addition to cable size, the tools also calculates the cable impedance and fault levels and the load at the load end of the cable. So the formula calculation method follows the procedure given as this standard. So we have definitions, that some of the definitions that we are going to use in this calculation. We have IZ, which is the current carrying capacity of the cable, that is the continuous service, that is in bracket when it is a continuous service under a definite installation condition. And then IT is the tabulated value of current. We said IZ is the carrying current capacity. IT is the tabulated value of the current, that is for the type of the cable, type of insulation, and at the ambient 30 degrees temperature. And then we have IB is the design current of the circuit expected in normal service. And then IN, the normal setting of any protective device. And then I2 is the current of the protective device. IA is the correction factor for the ambient temperature. IZ is the correction factor of the type of protective device. Those are the things that will get them there. Then IG is the correction factor of grouping circuit cables. Then CI, that is the correction factor of the thermal insulation. Then CT is the correction factor of the operating temperature. So you can see wherever we have the C, we have the correction. C is for correction. And CA, the small a, the subscript A is for ambient. The subscript C is for the protective device. The subscript G is for the grouping sizing. The subscript T is for the subscript I is the thermal temperature, is the thermal insulation. And then T, the subscript T for the CT is the correction factor for operating of the temperature, the conductor. So NP is the number of cables in parallel. TP is the maximum permitted operating temperature. So those are some of the basic things that we'll use in calculation. So when we want to get the current capacity, how do we do it? So by considering any correction factors, the tabulated current of the cable installed in a given situation can be found. So one of the tabulated values of current is found, that is the cable size determined by selecting the next largest cross-sectional area in the lookup tables. So for single circuits, you can see that IT is IN, and we already said IN what IN is, and these things can be measured. For group where simultaneous overload is possible, then IT should be greater or equal to the IN over this after what we've calculated there. So for groups not liable to stimulus overload, that is the maximum of is there, then the IT is equals to, no, that is a formula that is completed. So these are some of the calculations that we'll find in site. Sometimes you go to site and you are told to calculate the cable that is perfect, or the cable that suits a certain situation. So these are some of the formulas that you'll be able to use there. And we will do some example of this so that we calculate exactly what we are talking about. So when we are calculating the voltage drop, and voltage drop, remember voltage V is equals to IR, where R is the resistance and I is the current. So if we want to get the voltage drop, that is the voltage drop calculation, consider both the power factor of the system and the correction factor of that cable operated standards. So the tables of 4D, 1B, and of 4J4B is the standard given voltage drops. Be able to see these tables later on. And the resistance, you can see the voltage drops is the resistance and the reactive resistance, and the resistive and the reactive. So the resistive is R and the reactive is X. So all of them are resistant. So when they are multiplied by the correction factor, then we multiply by current, we'll get the total voltage drop. So the calculated voltage drop is given by this. See, this is the common formula for the calculated voltage drop. So the temperature correction factor is only applied to the resistance and is given by this formula. So you can make CT a subject and you get it. So note that the tool carries out all the calculations in complex form. And for instance, when you go to the industry, when you find yourself in the industry, some of these things, you will have some formulas. You will have some softwares that have already been developed to be able to calculate these formulas. So it's not a big deal that you'll get them. And sometimes the company, you will get the company has already purchased these softwares that it can enable in the calculation. We also calculate the fault level. That is, the fault level that withstand rating of the cable is determined by using the adiabatic equation. You can see the adiabatic equation where S is equals to the root of I squared T over K, where S is the cable cross-section area and I is the fault current of the flow. Remember, we are calculating fault level. T is the operating time of the protective device, and K is the factor related to the conductor material and insulation. Then frequently asked questions. What are the frequently asked questions? Now, additional parallel cables are automatically added to group derating. That is, you don't need to increase this manually. So all you can click and ignore the checkbox. I said it is a software. So that software, you just have to feed these values. When they say the cross-section area, you have to measure. That one you can measure. The fault current is also measured. And the protective device time, you can also time that. And the factor is normally given. You can see the factor is given as this from the tables. So all these things are things that are already there pre-hand. So we ask ourselves, what exactly is the number of circuits or cables that are needed in an installation? Sometimes I said that you need to do an installation, and you ask yourself that if I want to do a 3-bedroom house, what are this number of circuits that I need, or what are the number of cables, or what is the amount of cable that I will need to do a specific installation? So a group derating takes into account heat generated by the adjacent cables. So each circuit is usually supplied by one cable, and the number of circuits will equal the number of cables. So sometimes several cables are run parallel for a single circuit, and it's where this will increase the total number of cables. That is the group derating. That is the cable sizing guide. You can see from this picture, this is an example of a cable. This is a 4-wire cable which has the red, yellow. This is a 3-phase, but it has the neutral in each. Maybe this is a supply cable that is used to supply power to a distribution board. This is how it looks like. If you look keenly into this cable, because this cable, the width or the distance or the diameter for this cable is too thick, the cable cannot be one. You remember, we normally have singles and we have stradded. Stradded are these ones that have several strands to make maybe a single conductor, like maybe the live conductor or the neutral conductor. But when you look keenly, you see several strands being put to make one conductor. So this is done for even the bending, for possibility to be able to bend or to do anything. Okay, so when you look at this, then the sizing, cable sizing is very key when it comes to electrical installation. So the proper size helps avoid overloading and or underloading of cables. Overloading of cables may lead to damage of cables and in some cases heating that may cause electrical fire. So we say that the cable size is a very important thing. Knowing the cable size, what is the cable size of a certain cable? So knowing the size of the cable is very important. Sometimes maybe you want to load. Before you decide which cable that you are going to use or which size of cable you are going to use, you have to know the loading. Like for example, if you have a house, you want to use an iron box, you want to use a heater, you want to use a cooker, you want to use all those heavy things. And then the cable sizing it cannot just be 1.5. It has to be even more than 2.5 because of the amount of load that you need. So proper sizing helps avoid overloading and underloading of cables. So overloading cables may lead to damage of cables and in some cases heating. That may cause electrical fire. So under risk that are electrical fire. So underloading is going to incur unnecessary cable costs because when you underload also you are buying a very big cable for a load that is too small, then you are buying a cable that is not worth that work. So for a building service there are certain risks that are used. For example, lighting circuits are powered by say 1.5 millimeter square and the size of cable. So typical house sockets are wired by 2.5 millimeter square cable, etc. So experienced engineers also know and you cannot use 1.5 or 2.5 cable on your consumer unit or distribution board. That is very obvious. And this one calls also for experience. After you've done this work for quite some time, you will realize that after you are used to this, please mute your mic. Good. After you've done this work for quite some time and you are used to this work, you will just know by default that you cannot use a 1.5 cable to supply your distribution board. Why can't you use your 1.5 cable to supply your distribution board? It's because the amount of load that is expected for you that is supposed to be consumed using the distribution board. For example, a distribution board distributes power to like for example to different floors. Mostly distribution boards are used in storage houses. You cannot get a distribution board in a single unit. A single unit meaning a single household. Single household normally use consumer units. Consumer units are used to supply a single unit. But for a storage house is a house that has different floors. Different floors is a combination of several units put together to form a floor. So when these things are being used, when you are wiring a distribution board, of course, we have to use a cable like 10 millimeters. We have to supply power, a cable that is more than that, because of the loading. This distribution board will not supply a single house. It will supply several houses. And in the process of supplying these several houses, so it means that you need a lot of energy. You need a lot of power. And the more power that you need, the more the size of the cable that is needed. So this regard the load of the current calculations. So even though you load calculations may imply that 2.5 millimeter square cable is sufficient for power, even 10 millimeter cable, the diversity must also be taken into consideration. This helps in preventing the oversizing of cables. So for example, you will say that I have a single unit that I want to supply power, but currently I only have a TV, a television, and maybe some lighting points. But you forget that in future you might want to expand your loading. You might want to incorporate a cooker there. You might want to incorporate a washing machine there. So when you are doing these calculations, when the calculations are being done for these installations, we have to make sure that it is taken into consideration that in case of future load growth, that is what we mean. In case of future load growth, what is supposed to happen? So because of that, we have to make sure that when you are doing the design, and I said, as I had started, I said that there are several softwares that are in the market that will help us to calculate the cable size. You just put the loading, and after putting the loading, it will be able to generate the size of the cable that you need for a specific installation. So as a design engineer, which I know most of you people are going to land there, as a design engineer, you're supposed to know that this room is supposed to be used for this work. Maybe I'm doing a wiring system for an institution, like a workshop, like classrooms. You know, these are things that can change to be anything. There are rooms that can be changed to be workshop, They can change to work to be classrooms. So whatever you do is you make sure that anytime you're doing these calculations or the cable sizing, you give an allowance. That is, it is not too easy to predict the load growth, but some engineers use a value ranging from 15 to 25%. You give a 15% and 15 to 25% expanding, so that if this cable is up to, for now, is supposed to carry this amount of load, like 100 watts at a go, then I'm going to give an allowance of about 25%. So if I was to use the 2.5 millimeter square, so I'll not use 2.5, but I'll use 4.0. And remember, the cable sizing as we move the ranges, we normally have 1.0, then next is 1.5, then 2.5, then 4.0. We normally don't have 3 and so on and so on in between there. We just go direct to 4.0. So if you think that your 2.0 is enough for now, then you can give a room for the future and ask yourself, what other loads what other load growth are expected in this room. So when you realize and notice that the load groups that are expected in the room, so what do? You anticipate for the future and extend the loading, meaning you increase the cable sizes. So let us look at this table. This is a typical cable size for the typical loadings. So the type of circuit is there. For example, for a single phase, so we have a single phase maximum power. This is the cable sizing area cross section, and this one is the maximum power that it can carry, and the protective device that you can use, and the maximum loading of the protective device. So for example, if I'm using fixed lighting, these are lighting points like the normal lighting that we use. What is the expected cable size that I use? The expected cable size is normally 1.5. But now if I'm expecting a higher loading in future, if I'm expecting to add some more loading, for security purposes, I can use 2.5, but 1.5 can perfectly work very well. So what is the maximum power that is expected for lighting? The maximum power that is expected for lighting is 2,300 watts. What is the protective device? Of course, the protective device there is the circuit breaker, and the circuit breaker has a fuse inside. So the amount or the amperage of the circuit breaker can range from 10 to 16 amps. But some are normally very mean. They even use 6 amperes. You can imagine 6 amperes is very small. So and we talk about maybe these circuit breakers that are being used by people like these people who the people who do commercial houses or residential houses for renting. So they normally need like using these circuit breakers. So the moment you put this circuit breaker, it limits. So any extra load, any load that takes a current that is more than maybe this, if you, for example, use a 10 ampere circuit breaker, any device that can use more than a 10 amperes load, it will energize the circuit breaker, or it will force the circuit breaker to trip. So that is the work of that circuit breaker. So you can see now we have around 10 to 16 socket outlets in a house. What cable is perfect for that? The cable that is perfect for that is 2.5 millimeter square. And then we ask ourselves, what about if we are anticipating or we are expecting a future increase of load? Then we can say it can come to 4 millimeters squared, and then the amount of power, that the exceeding power or the maximum power, the maximum power can be 4,600 watts, and the circuit breaker that is needed there can be between 20 to 25 amperes. Those are now the standard things. Individual load circuits. Now, on the individual load circuits, we can have now like a water heater. This one now are for a specific use. They're not common for all residential housings. So dishwashing machine, it can use 2.5 millimeters or up to 4 millimeters. Cloth washing machine, we have a cooker units, we have electrical space heaters. Space heaters, these are heaters that are used to warm the environment. And the fuses that we need, you can see the circuit breaker that it needs between 32 to 40 amperes. And and also the cloth washing machine, you can see the circuit breaker that it needs. You will see that difference there. So note that the cross-section area of aluminum conductors are shown in brackets. You can see there. Now the load, device, and cable characteristics. Now the device rating. Now you can see the characteristics of a device. That is the load. We can say IB, the device rating IN, the IZ, the current carrying conductor, the tabulated current capacity. You can remember those factors that we listed on the definitions. So where the IB is the design current that is determined for the load to be connected, and then IN is the rated current of the current setting of the protective device. Then IZ is the current carrying capacity of the cable for continuous service in this particular installation condition. Okay. So that is a continuation. That IT is the tabulated current. We already talked about it. The IB is the design current. IN is the rated current. IZ and then IT. Now the cable selection. Sometimes we want to select the type of cable. Now before estimating the quantities of the required cables, we should understand some concepts about the cable selection. So the voltage level used, that is the type of loads we want to be serviced, that is the static, dynamic, heating loads, etc. As the type of loading may impact the cable sizing, that is the coating and the armoring as well. So the distance and the route of the laying that is determine the type of conductor is based on either transmission as via overhead line or the underground. I had stated this earlier that depending on the route that is going to, the cable is going to follow. Like for example, the overhead lines can use these copper conductors without insulation. But for the underground lines, they use the copper conductors, but they have to be insulated because of the mechanical damage. Sometimes there are heavy machines, like even tractors passing through the cable, or even some digging that is going. So it is normally protected so that in case of anything, you'll get the cable is protected. And then the configuration to be followed either using transformers to step up or step down for long distance or directly connecting for the loads. So it will be useful to determine the lifetime of the equipment and the importance of it to the system from economic point of view. So in order to select perfectly, now for an example, from the IEE regulations, and we said the IEE regulations are the ones that normally guide us. So the XLPE cables, copper cables, can withstand for 60 years at 86.5 degrees centigrade, and PVC can withstand for 40 years centigrade. So therefore it depends on the equipment you want to serve. So how to select the correct cross-section area of cables with particular single phase loads in mind. So you can see now calculating the right cable size. So there are 5 steps in calculating the right cable size of a cable for a particular loading. So these are as follows. So calculate the design, that is the design current. It is the normal current drawn by the load. So it is usually determined as follows. This is how we determine it. By IB is the watts over voltage. So the total wattage that is normally written is normally inscribed on the rating of the, maybe on the specification of that kind of apparatus divided by the voltage, that is the supply voltage. So 2 is select the type of current rating of the overcurrent device, that is IN. And then 3, apply the relevant correction factors to obtain the tabulated current. And then our 18, the correction factors are applied to situations with inhibited or cable from dissipating its heat caused by the normal flow of current through it. So therefore, the following correction factors is applicable and are as this. We have the ambient temperature. These are the very important things that have to be considered. And remember this formula, I had already given it to you before, that the ambient temperature CA, that is the factor that is obtained from the table that we had talked about, and it is a variable of fuse, that is the BS 3036 standard. We also need the grouping factor, that is the CG, the factor found for reference on the table, we have already said that, and used for where mineral installed cable are installed on perforated clay tray. Another one is the thermal insulation, that is the CI. And then reliable fuse factor, CR, and how to apply the correction factors. These are formula with some examples. So more correction factors will apply, the larger the value of it will be, and hence the larger the size of the cable we will require. So consequently, it is advantageous to avoid having to apply correction factors where possible by such measures as avoiding grouping of cables and avoiding contact of thermal insulation. So, however, the formula given above is used on the conception that the condition requiring the application of correction factors apply simultaneously on the same part of the cable along its route. So where a particular correction factors are appropriate on different parts, the cable along its route, each part can be treated separately. So this is a formula for voltage drop. You can see it there. So an example is here. A 6 kilowatt load is to be supplied by a 340 volts by a PVC sheathed and insulation twin and CPC conductor cable that is 8 meters in length. The cable is clipped on the surface through an area and an ambient temperature of 40 degrees, and it's grouped with the 3 other cables of similar size and loading. So the protection is by means of this. So calculate the minimum cable size required at all correction factors needed to apply here. So how do we go about that? So the first thing is we have to calculate the design current. And how do we design the design current is IB is what we said it is wattage over the voltage. So the wattage is we are already given the loading of that specific load, which is 6 kilowatts, which is 6,000 watts, divided by the voltage, which is the standard supply voltage, which is 230 volts, which is equal to 26 amperes. So that is the rated current or the design current. So the size of the BC that is 36 fuse required is the 30 amperes tabulated. So you normally equate this current loading to the BS, the standard. So these BS standards are normally standards that are given, and they're normally there for any calculations, and they are codes of insulation that are normally given. So when from the table, and that table is normally given, so in case of an exam, you'll be able to be supplied the table so that you can be able to calculate. So CA, we said is the correction of the ambient temperature, that is ECA, is 0.94. That is from the table, of course. And then we have the grouping correction factor is 0.65. And then we have the correction factor from the BS standard for the fuse is 0.725. So when we calculate the current, the temperature, the current, the rating temperature current, we'll get thermal temperature current is IN, which has to be greater or equal to that. So from the formula, we realize that we are getting 30 amperes. That is the IN. We said that is the rated from the BS standards. So when we calculate and we insert everything in the table, we'll get that it is IT has to be greater or equal to 67.7 amperes. So from the table, we see at the column, the table we said we'll get them at the IE standards. Select the 16 millimeters a cable, which will take 85 amperes. So the best cable for that work is a 60 millimeter cable size. So the voltage drop is here, and you calculate using that formula and you get 0.85. So I'll be able to forward these notes for you so that you can go through this calculation again and try to follow it up. An example 2 is there. I'll expect you guys to go through it. And in case of a question, you will ask me when we will be coming back after the discussion. We will be breaking for the discussion for around 40 minutes. So when we'll be coming back, we'll be able to tell me any problem that you encountered from the calculation. So the final circuit voltage drop limitations, you can see it's calculated there. The National Electrical Code recommends that for reasonable efficiency of operation that the maximum total voltage drop over both feeders and branches circuits or to the farthest outlet power point, that is the heating and the lighting loads, should not exceed 5% of the normal system voltage. So also conductors for feeders and for conductors of branch circuits should be sized to prevent voltage drop exceeding 3% at the farthest outlet. So if voltage spread exceeds acceptable limits or is not suitable for the critical load, any of the four basic ways are used to reduce the spread. That is, number one, the length of the conductor. Sometimes the length of the conductor is reduced, that is to lower the voltage drop, and should be shortened, and the length of the conductor carrying higher voltage should be lightened. Should be made to be lighter. You realize that, for example, for instance, when normal installation is being done. So, for example, when we are wiring something like a service cable. When the Kenya Power people come to drop the cable, they normally say that the service cable should not exceed a distance of 30 meters. Why do we need this? This is because we will need to lower the voltage drop. So the more we lower the voltage drop, the more the efficiency and the working of the cable. So normally when it exceeds 30 meters, so the best option there is normally to increase a post so that the cable can be shortened. That is now a basic way of shortening the cable. Another thing is the system impedance should be reduced. Impedance, remember, it is the resistance, that is the inductance in the cable. And then the voltage regulator should be installed on buses and feeders to compensate for the voltage drop. And then the capacitors should be installed to improve the power factor because a smaller currents flow as power factor is increased. So up to that point, we are done with the first slide, and I want to give a small introduction for the next slide before we can break for discussion. So current rating of a cable. What is the current rating and how does it affect the cable size? You remember we have been calculating how to get the exact cable size, and I said that these calculations are just meant for your classwork and schoolwork and maybe the examination, but when you go to the field, softwares have already been developed. Softwares have been developed that are able to these softwares are able to facilitate the calculation, the automatic calculation of the cable sizes. So it is good for you guys to understand the manual way of calculating before you can be able to get into the software, because you need to understand the concepts that come with them. So the definition on cable rating, that is the current rating. Current rating of a cable, that is the current rating of a cable, is defined as the maximum current carrying capacity of the power cable under normal operating conditions. That is the current rating of power cables decided the upper limit of the power transfer by a cable. It mostly depends on the insulation temperature and electrical resistance of the conductor. So the cable rating is classified under three headings, which are normal maximum continuous current rating. That is the normal maximum continuous current rating. Another one is the overload overcurrent rating, and then the short circuit rating. These are the basic calculations that will enable the calculation of the current rating. So classifications of current rating or cables, that is the different types of current rating of cables, are explained below in details. So we have the normal or safe current carrying capacity. That is the normal or the safe current carrying capacity depends on some factors. That is some of the important factors are the minimum conductor operating temperature, the heat dissipating properties of the cable, the condition of insulation, For calculating the current carrying capacity of the cable, that is the thermal resistance, the sheath of the cable, the sheath I said is the outer covering on the insulation of the cable, are neglected during this calculation. And then the heat generated in the cable is due to various losses in conduct, which is conducted in the air or the ground through various paths. Now, these paths offer various resistance and flow of heat. So in the three-phase cables, all the three conductors are at the same temperature. The heat produced flows outwards through the dielectric or three parallel paths, and the sheath may be assumed to be the grouping G, C1, C2, and C3, then passes through the bedding resistance GB, which is the metallic armoring serving the resistance. So finally, it passes through the surrounding air or the ground, depending upon the method of the insulation cable. So I want us to go for a break. And in this break, people are supposed to join in the discussion. There are some discussion questions that are there, and remember, your participation in the discussion also adds up to your final grading in the semester, when we'll be adding up everything that you do. Participation in the discussion, in the conferencing, the cards, the assignments, the attendance of the conferencing are very important to enable you to proceed to the next semester. So I want people to unmute their mics so that you can at least say something. Unmute your mics. I want to hear people tell me something before we can go for the discussion, and then come back after 40 minutes so that we can finish the other part of the lesson. Can I hear people say something? Maybe something you didn't understand, a complaint, or anything that you're experiencing that you have not been able to communicate. Can I hear people talk? Steven, Kachoki, Muigai, I can see you only joined in listen only. Try to put your mic on so that I can hear you people talk. I want to hear people talk. Yes, Steven. I want to listen to people. Kachoki.
Yes.
Yes, I want to hear people say something. Maybe a comment or anything that you didn't understand before we can go to the discussion.
Okay. I have to understand.
You have understood everything.
Yeah, I'm good.
Okay, what about the others? So let us go for the discussion.
Yeah.
In the same place that you accessed the portal, the classwork. So we are going there, and we are going to join in the discussion. I'll be there waiting for you to discuss. So we are going to participate in the discussion for the next 40 minutes. So we are going to come back at exactly 12. We'll come back at exactly 12:50. I think 12:50 is okay.
Yeah.
Yeah. Chris Mugai is saying that my mic haifanyi. Okay, haifanyi, but let us go to the discussion. It's okay. We understand. So let us go to the discussion. And then after the discussion, we are going to come back here at 12:50 so that we finish that part of the lesson. Hope that is okay. Okay. So I'm taking you to the discussion, and I'll stop. Let me resume recording. We are doing cable selection. Now we have already talked about rating. We need to know the cable rating, and we need to know how to do the current cable rating. So cable selection and application. After knowing how to calculate the cable size, the type of cable to be used at a specific place, The loading of a cable. I gave you the table that showed the loading of different cables. Now we need to select cables. Now cable selection and application. How do we select a specific cable? Now it's essential to know cable construction, characteristics, and rating to understand problems related to cable systems. However, to correctly select a cable system and assure its satisfactory operation, additional knowledge is required. This knowledge may consist of service conditions, type and load service, mode of operation and maintenance, and the like. So we have key factors to the correct cable selection and application. You can now look at this. Look at this picture. You can see terminations. Now, like for example, depending on where the cable is going to be used, for you to be able to select the exact cable or correct cable selection, you have to know how you're going to terminate your cable. There are key factors. There are key factors that we are going to take. That is the cable insulation, the cable construction, how is it constructed, the cable and voltage operation, the cable sizing, and the shield operation. So key the key of the successful operation of the cable system is to select the most suitable cable for the application. So to make the correct installation and perform the required maintenance. So when you look at this drawing, this picture, it is a termination of cables. You can see that the termination done here is very perfect and the coding is put. So the red is there to include that this is the live cable, and the blue is there to include that is neutral, and the white is there also to include for the earthing. You can see how the earthing, the bus bars are the different bus bars are there and how it is being tapped. You can see the live tapping is there for the live cable. That is the bus bar, the topmost bus bar. This one is for the live. The following bus bar is for the blue, which is the the neutral. And finally, this one is for the earthing system. You can see I've zoomed it out so that you can see how it is installed. The cable lags, the way they are terminated, for easier termination, sometimes the termination can be a problem. So the cable lags are put there. It's a part of the insulation, and it can prevent any kind of short circuiting. So this is one of the perfect ways. So you can see this one. This one is the bonding that is done to different metallic parts that is done. So this is a perfect way of doing cable selection and using depending on the type of the use. So cable selection can be based upon the following 5 key factors. So we are now on the factors that affect the cable selection. We have the cable installation, the cable construction, the cable operation, that is the voltage and current, the cable size, and the shield requirements. Then we have the cable installation. So cables can be used for outdoor or indoor installations depending upon the distribution system and the load serviced. So a good understanding of local conditions, that is the installation crews, and maintenance personnel, is essential to ensure that the selected cable system will operate satisfactorily. So the main times cable installation is damaged and weakened during the installation by applying the incorrect plugs or tension. So sometimes when we are doing the cable selection, we have to select even how the termination will take place. So the designing of the conduit system not only should minimize the number of conduit bends and distance between the manholes, but also should specify the pulling tension. Sometimes a cable is being pulled, so it can affect the resistance, or it can. So you can see the conductor is there, the sheath, the armoring. All these are some of the strenuous things. So you can see the conductor is affected by the electric. The sheath can be affected by the bending, and the armoring can be affected by the cable surface. So let the thermal resistance of the thermal heat flow path be GE, i.e. G is the thermal resistance between the outer surface of the cable and the ambient, and the thermal resistance of the metallic portion, namely screens, sheath, and armoring, are negligible. Heat is generated due to the loss of in the core. So you can see the formula for calculating the current rating of, and then we have the resistance, where the AC resistance per unit length. These are the conductors. These are the factors. We said that is one of the factors in selecting the cable size or the type. And then we have overcurrent rating. The overcurrent rating and rating depends on the thermal conductors conditions of the cable. So the value of maximum or continuous current ratings of cable is supplied by manufacturers. So the rating valid for specified conductor conditions of installation, depth of laying, that is ground temperature and air temperature. So the short circuit rating: in short circuit conditions, the current flows through the cables many times at the full load value of the current. So that is the short circuit rating. All these things have to be put into consideration. And we say these are the factors we were discussing about. The factors the cable the 5 factors that affect the cable selection, or when you are selecting a cable. So we have talked about the cable insulation, we are the current rating, short circuiting rating, and also we have the cable selection and the application. So now when we want to select them and apply them, now like for example here, it's essential to know the cable construction characteristic rating and understand the problems related with the system. So however, the correctly selected a cable to assure the successful duration at that is operation, additional knowledge is required. So this knowledge may consist a service condition, that the type of load served, the mode of operation and maintenance, and like of things. So we have talked about that. We have the cable installation. Cable construction is also another factor. So that is factor number 2, cable installation. That is cable construction is another one. Then the conductors. Well, the conductors are materials such as copper, aluminum, which should be given consideration in regard with the workmanship, environment conditions, and maintenance. So the requirements of the aluminum conductors with regard to these factors are more critical than the copper conductors. So we also have the arrangement. That is, conductors can be arranged in form of single conductor or 3 conductor cable. When you say single conductor, it is one cable, that is one conductor separately, meaning the conductors are arranged separately, and the 3 conductors, like now the live, the neutral, and the earth, being sealed in one, that is called the twin with earth, or can also even have twin. So there are certain advantages and disadvantages of both these types of arrangements. So single conductors are easier to install, easier to splice, and allow formation of multiple cable circuits. So on the other hand, they have higher resistance than the 3 conductor core. So shielded single conductors carry high shield current, and construction and consideration must be given in preventing the overheating of the cables. So availability of the ground wire. We talked about the ground wire, which needs to have a lot of insulation. So the 3 conductor cable or a separate ground wire with single conductor cable is an important consideration. So since the ground conductor in the 3 conductor cable construction provides the lowest impedance path, it offers a good system ground. So similarly, a separate ground in the same conduit as the power conductors provides a better ground turn path than a ground path via the equipment or the building steel. Another one is the insulation and finish covering. That is another thing that has to be considered. That is the insulation and the selection of the cable insulation and finish covering is normally based on the type of insulation, that is the ambient operating temperature. We talked about the ambient temperature. We have the service conditions, the type of loading served. These are the major issues there, and other criteria as applicable. So in many insulation, unusual conditions may be prevalent, such as corrosive atmosphere, high ambient temperature, insect and rodent hazard, presence of oil and solvents, presence of ozone, and extreme cold. So in certain applications, the 2 or more of these usual conditions may be present, in which case the selection of suitable cable become more difficult. Cable operation is also another thing. That is, insulation of cables must be able to withstand the voltage stress. That is the insulation that we are talking about. Some of the cables that are being manufactured these days are very fake. You get that the insulation can easily be peeled off even by just stretching the cable. So for a good cable, it has to withstand the voltage stress so experienced during the normal and abnormal operating conditions. Therefore, the selection of the cable insulation should be made on the basis of applicable phase-to-phase voltage and general system category, which are classified in either 100%, 133%, or 173% insulation level. These insulation level discussed are as follows. 100 level means that the cable in its category may be applicable where the system is provided with relay protection, which normally clears the ground fault. That is, it has to have the relay protection. What about the 133? The 133 means that the cable in this category may be applied where the system is provided with the relay protection, which normally clears the ground fault within 1 hour. So this category is usually referred to as the low resistance grounded or ungrounded system. And then another one is the 173% level, which is a cable that is category may be applied where the time needed to de-energize the ground fault is indefinite. This level is recommended for underground and the resonant ground system. The current capacity that the cable needs to carry is determined by the load it serves. So those are the formulas for calculating. We had already discussed those formulas. Another thing that we have to consider is the cable size. That is, the selection of the cable size is based upon the following factors. That is the current carrying capacity, the voltage regulation, short circuiting. We have already talked about that. And then the current carrying capacitor, we explained that. Voltage regulation, short circuit rating. And then shielding is another factor. That is, in selection and in selecting and applying cables with medium voltage, a major consideration involves whether the cable should be shielded or not shielded. So what does this shielding mean? The shielding means that this is now the extra insulation, the type of insulation that is being used. That is the condition under which shield cable is to be selected and applied is explained in the following discussion. That is, the application of shield cable involves the following considerations. Number one, the type of insulation system, whether the system is neutral, ground, or ungrounded, or the safety and the reliability of the requirement. So in power systems, there are no shield or metallic covering. So the electric field is partly in the air and partly in the insulation system. So those are major things. Now look at this cable. This is an example, a typical example of a cable that has been shielded. So in case where portable cables, that is portable assemblies are exposed, overheat cable installations are to be used and may be handled by personnel. So serious safety hazard may exist if non-shielded cable is used. So when you look at this, most of the time in your exams, you'll get such a thing and you'll be told to explain, draw and explain, name the parts and explain the functions of these different parts. So when you look at it, there are 5 fundamental constituents that make a cable. That is, we have the conductor itself. You can see the conductor. I said the conductor can be stranded or can be a whole. A stranded is meaning it has strips, like now different pieces making one strand. That is a stranded. So for example, this one has strands, a lot of strands making one conductor. And then it has a shield. You can see the shield there. And then another one is a filler. You can see a filler in between this shield and the primary insulation. So the primary insulation also has the color. And then shielding should be considered for a non-metallic cable operating in excessive operating in excess of the 2 kilovolts, where any of the following conditions exist. Okay. Another one is the connection of aerial wires. I hope you guys are getting me. If you're not getting me, you can write on the public chat, because I've experienced some disturbance. I hope people are following. Okay, so these are the cable parts. There was a small disturbance, but I now hope we are together. So you can see this jacket installation. This is now the outer covering, which is normally as color codes like now black, blue, or whatever the color. So all this, the function of the shield, all this, the shield and the filter is for mechanical strength, the mechanical strength that the cable needs. So you can imagine that the moment you can expose all this until you come to the conductor itself, it is very difficult. So that is why this one is very well protected. So when you are choosing the cable type, you can also look at how it is constructed to make sure that it's perfectly well made. And then we have insulation shield must be grounded at least at one end, and preferably at two or more points. So the cable shield must be grounded also at all terminations, splices, and tabs that stress cones. The shield should be operated at ground potential. So you can see now the grounding, the shielding that we are talking about, the cable type, that is the sheathed cable. A single conductor normally has grounded at 5 kilovolts, 5 kilovolts, 5 kilovolts, 5 kilovolts for 3 conductor. The interlock also has 555. The Fabrius covered cable, that is 222, and then an unzone resistance also 222. Then ozone resistance, those are the ratings. So factors affecting bare conductor on current ratings. To examine factors affecting the steady state and transient current of the ratings. Once you guys, you'll be able to read them, because I'm going to forward these notes for you. So you can see this table also dealing with the different temperatures, the ambient temperatures, the maximum continuous operating temperature, the maximum short time operating, the initial conductor temperature for prior to transient, and then environment conditions. For conductors, as steady state conditions are there. A curve is there that is constructed to show the conductor operating with temperature, depending on different types of cables. Okay. I will not talk about that. But you guys can go through them. I want to go to a certain slide before we finish. So I want to show you some pictures of practical cables that we have been talking about. I'm opening up. These are the IEC standards that we were talking about, and the tables. These are the tables that I told you that I was to show you. So you look at them at your own time. Definitions, general, normal value, approximate value. These are calculations and definitions and tests. Voltage drop designations. Technical data and cable parameters. These are now the formulas that we were talking about. I'm just showing you so that you guys can be able go through them. Technical data and cable parameters. These are still other formulas. Now the rating factors. The current ratings that we are talking about are here. The cables are here, the short cables, the cords, and the tables are here. The cross-section area, as we are talked about, are here, and how to calculate the copper conductors and the XPL cables. All of them are here. How to know the ambient temperature, the duration in seconds, and the time that it takes. Transfer current. All the tables that we are talking about are here. So I'd like you to go and follow up with them. So overhead cables, you can. Yes, Gachoki. Okay. Aluminum conductors. I'm now showing you the description and the codes and the tables that we were talking about. Remember, we had talked about these tables and how we can pick them and know the exact size of conductor that you need, depending on the supply. These are the different types of cables that we have. All aluminum alloy conductors. That is the AAAC cables are there. You can see now aluminum conductors still reinforced. These are how they look like. Aluminum conductor still reinforced, still they are there. Remember this one will be, these are the codes, the product codes, how they appear in the market. All those are the codes that we were talking about earlier on. All those are the codes. So up to that point, I'll share this one with you so that you guys will be able to look at all the tables, and I'll also send you to the portal the notes on the IEE regulation to be able to show you what the IEE regulations require in the color codings, or the cable types. So I want us to end our class there, and in case of anything, can I hear